Hello and welcome. In this video, now we will deal with the equivalent circuit of the induction machine in order to better understand its behavior, and therefore we also know how we can use its behavior to better adapt to wind turbines. So we always look only to one phase. Even we have three-phase systems, in the equivalent circuit we only consider one phase. So first what we see here is the rotor circuit, the inductance and the resistance of the rotor coil, with X2 equivalent to omega times L2, and that is equivalent to 2P F2 times L2. And there we already see X2 is not a constant. It has a maximum at standstill, and then the rotor frequency equals the mains frequency, and X2 becomes 0 when the rotor speed reaches the rotating field speed, and then F2 is equal to 0. So we have the X2 is equivalent to the slip S time X to 0, and we have U2 is equivalent to the slip S times U to 0. And then we have the impedance Z is the square root of R2 to the square plus in brackets S times X to 0 to the square. And we have the rotor current. I2 is equivalent to S U to 0 divided by this square root R2 to the square plus in brackets S X to 0 to the square. In literature, it is more common that we divide all those figures by S, and then we get the relations we see here in this graph. And therefore the impedance Z is then equivalent to the square root of R2 divided by S to the square plus X to 0 to the square. And the rotor current I2 is equivalent to U to 0 divided by this square root we just have seen. So now we need to add the stator, and even in a no load condition there is a current I0 in the stator. A reactive current is representing the magnetic flux, and the real current is representing the iron and friction losses. What is important here is that the components of the rotor circuit are no longer the measurable variables in the rotor circuit itself, but it's the variables measurable via the air gap at the terminals of the stator. And that's the reason why now this R2 divided by S has this indice 1 on top, and also the X to 0 has this indice 1 on top. Finally, we need to add this R1 and X1 for the stator. And now we do some tricks, and as this R, Fe and the friction losses is much bigger than the R1 and the R21 divided by S, and also the X mu is much bigger than the X1 and the X20, we can shift this vertical branch to the left and these resistances and impedances to the right. Then we also can eliminate this R1 because it's much smaller than the R21 divided by S. And then we combine X1 and X20 to the 1 to this X. Now we can have a look to our induction generator, how it operates as motor. And we again see the behavior in relation to the slip S on the horizontal of the diagram. And there we see the stator current is increasing with the slip S, and a bit less is always then the current of the rotor, as we have a few losses here in the air gap that is the vertical branch here. What is quite important is the moment here. And there we see we have a very steep increase of the mechanical moment, and then it reaches the maximum at a certain point, and with increasing slips it is again decreasing. That's the same with the cosine phi. It's increasing, has a maximum, and decreasing again. And also the efficiency of the motor has a maximum at quite small slips and then is decreasing again. But we are interested more in generators, and therefore with negative slips also the moment is getting negative but has the same behavior. A steep increase and then a maximum at a certain level of the slip S, and then it's decreasing again from the absolute value. Again, we have maximum efficiency at small slips, and we also have this behavior of the cosine phi. That means the cosine phi is getting a maximum where the requirement of inductive power is at its minimum, and then the cosine phi is decreasing again. And to be complete, also the currents we can mention here. When we look to the turning moment and rotation field power, they are proportional to each other. That means the PD is equivalent to the moment m times 2p and d, and then we convert that into the moment m is equivalent to pd divided by 2p and d. And then with the elements of the equivalent circuit, we can transform this equation to what you see there on the right side. And this term is getting at its maximum when the R2 divided by the S is the same like the reactance X. That means when R21 divided by S is equivalent X. And the corresponding slip where it's getting maximum is then the pull-out slip is equivalent R21 divided by X. And this pull-out moment is then the PD for the pull-out divided by 2p and d is equivalent the I21 to the square times R21 divided by the pull-out slip, and always then times this free, because we have this equivalent circuit only single phase, but in reality we have three phases. And then we get this new expression that we see in the next line. And when we add there this R21 divided by S equivalent to X, we get this relation for the pull-out moment is equivalent to 3 divided p 2p and d times u1 to the square divided by 2x. And that is quite impressive because the maximum moment is not dependent on the rotor active resistance. But when we look to the position where the moment is getting its maximum, the corresponding pull-out slip, that depends on the resistance. And that we later will use for our wind turbine operation. Now we put into relation the mechanical moment to its maximum, the pull-out moment, and then we reach this expression we see there in this equation. And there we already can delete some of the values, but it's still quite complex. And then we divide and multiply both sides with 2x. We result this expression. And then we add the multiplication by s divided by s, and resulting in this expression. It's now much easier, but still not in the end. And then we divide once more by x times R2, 1. And then we result in this expression here that the moment in relation to the pull-out moment is equivalent to 2 divided by the pull-out slip divided by the slip plus the slip divided by the pull-out slip. And because that is a quite famous equation, quite often used to display also the behavior of induction generators, It is called the Cloche formula. And in the next video we will then have a look how we can use this behavior of the induction generator in order to adopt better our wind turbines to the typical wind behavior. Thank you very much.